This lecture is going to introduce how you can use ridge regression as a method for regularization. So let's go back to this figure that we've discussed in the past. And so with most data mining models, there's going to be uh, a way to control how complex the model is. Okay, so we've seen a couple examples of this. Remember, we had an example with some polynomials. And so the degree of the polynomial is one way to control the complexity. So I could start out with a very simple polynomial, like a constant, right? So just having an intercept. Or I could have a first degree polynomial or a line or a second degree, third degree, all the way up to, we went up to like 6-degree polynomials. And that's going to increase the flexibility of the model, the complexity of the model. Now we saw in that example that, I can show you the example right here. When we had, a first degree polynomial or a line, it fit the data very well. As we increased the complexity, we started to capitalize on chance, and the model overfitted the data. So on a test set, this blue model would perform very poorly. So it looks like it does really well. This was the mean squared error. But when we went off and tried a test set of 10,000 cases from the same model, the MSE was a disaster. Compare that with linear regression, where linear fit, you get an MSE of around 1, and that holds up pretty well when you have that big test set. All right, so the point is that we have this dial, and we can increase the number of increase the complexity or decrease it, and on a test set, the model's going to get better for a while, and then it's going to get worse. All right. So our goal is to find this model with the optimum level of complexity. So where does that test sample prediction error bottom out? All right, so that's our goal. Now the question is, how do I control the complexity of a model? So we've seen one example with polynomials as one example. We've seen another example, which is forward selection regression, right? So what was forward selection about? Well, you start out with nothing in the model, so you have just an intercept, and then you keep adding one predictor at a time, and each time you add a predictor, the model gets more complex until you have all P predictors in. And we saw in the second example here how that could lead to problems. All right, so stepwise regression, forward selection, backward selection, these are all methods for sort of managing the gap between low and high level complexity. Now we're going to talk about a completely different approach, which is shrinkage. So instead of having variables that we toss out of the model, that's what selection is all about, we're going to allow the predictors to stay in the model, but they're going to have less, less say. Okay, so we're going to shrink their betas. Now, in order to estimate such a model, we're going to use penalized least squares. So this is the objective function for penalized least squares. The first part of this objective function should look very familiar to you. This is just your least squares objective function. So take y sub I minus the predicted values, square it, add it up, and you get RSS. What's new is this term over here. So this term is lambda times the sum of the betas squared. I think the sum of the betas squared has kind of an interesting interpretation. Let's go over to PowerPoint for a second, where I sketched out a little graph. We can think of betas as being in a beta space. Okay, so this is the beta 1 axis, this is the beta 2 axis, and let's say I got some parameter estimates, so beta 1, beta 2. So how would I find the length of this beta 1, beta 2 vector? Well, we'd use the Pythagorean theorem, right? Which means you would take beta 1 squared plus beta 2 squared. So a squared plus b squared equals c squared. So if I take beta 1 squared plus beta 2 squared, I get the length of this beta vector squared. All right, so that's the way to think about this term. This is the squared length of your slope vector. Now, we're imposing a penalty term, lambda. Now, this lambda is under your control, and it's this lambda that's going to allow you to, control the model complexity. Okay, to see how this works, let's just take lambda equal to 0 for a second. So if I take lambda equal to 0, the penalty term disappears, and we're left with basic OLS, which means we have all the predictors in the model. So there's no regularization, no shrinkage whatsoever. Okay, well, let's consider another extreme. So let's say I decide to make lambda really big. So I make lambda 100 trillion or some enormous number, the biggest number I could possibly think of. So what that means is whenever these betas have any length at all, that very small length is going to get multiplied by an absolutely massive number, and this objective function that we're going to try to minimize is going to blow up. So what would any good optimization algorithm do? Well, it would shrink these betas to 0, because if these betas are all 0, add up a bunch of zeros, multiply zeros by a very big number, you get 0, and there is no penalty. All right, so what that's saying is, if I make lambda really big, all of my betas from 1 to p are going to go to 0. Well, what am I left with? I'm left with just the intercept. Okay, so that's the lowest complexity model we could possibly have, is where I just have an intercept in the model. So lambda equal to giant is over here, lambda equal to 0 is over here. Our goal is to choose what we're going to call lambda min. Lambda min is going to be the value that gives the lowest test set error. All right, so that's what ridge regression does. Now there's a lot of very interesting theory behind this that I'm not going to discuss in this short video. I do want to mention one more real important consideration. Okay, the important consideration is this. These betas all receive the same penalty, lambda. Okay, so since they're receiving the same penalty, this is going to be scale dependent. So in other words, let's say I have x1 measured in centimeters and x2 measured in centimeters. And then let's say I do something like change the units of measurement just on x1. So if I change the units on x1 to, say, millimeters, well, all the x's are now have a bigger scale, the betas get smaller, and we don't penalize x1 that much. Likewise, if I change the units to meters on x1, well, then the slope's going to get bigger, and we're going to penalize that direction much more. So in other words, it's not, it's going to be dependent on the units we choose, and that's very undesirable. Therefore, we usually standardize the variables before we use ridge regression. All right, let's go look at a really famous example. This is called the body fat example, and it's taken from a book I used to teach from. And so you can click on this if you want to read more about this this example. We're trying to estimate the body fat of a patient, but measuring body fat is complicated because you have to, I believe you have to submerge them in a body of water. And so most people don't want to go into a body of water when you go to the doctor. So we're seeking an easier way to quantify body fat. So we're going to measure some other variables. We're going to measure the tricep skin fold thickness, the thigh circumference, and the mid-arm circumference. So these are 3 things that we can easily measure. We have a training sample with about 20 cases where we have a gold standard measure of body fat in addition to these three, let's call them proxy measures. And so my goal is to relate these three proxy measures to the dependent variable, which is body fat. So if I go into the doctor's office, they could then just measure my tricep skin fold thickness, thigh circumference, and mid-arm circumference, pop it into the regression model, and if the regression model is accurate, they could know my body fat. All right, well, let's go look at a scatter plot matrix. Now what you're going to see is that tricep skin fold thickness has a strong positive relationship with body fat. So the thicker my skin fold is, the more body fat I have. Likewise, we see a strong positive association between thigh circumference and body fat. There's not much of a relationship with mid-arm circumference. Now, what we should also note is that there's a very strong positive correlation between my tricep skin fold thickness and my thigh circumference. So those two measures are almost proxies for one another. That's reflected in the correlation matrix. So strong positive correlations between x1 and x2 and y. However, x1 and x2 are pretty correlated with each other. Now, we put this into a regression model. What you're going to see is you get a sign flip. Okay, so look at that big negative 2.86 for x2. So the interpretation of this is, well, the larger my thighs, the lower my body fat. And of course, that seems like nonsense. What's happening here is these two variables, they basically go in the same direction. But, if we put a negative sign on this, that's fine as long as we make x1 way bigger. So if x1 has a much stronger effect, we can get away with having a negative coefficient on x2. But that seems all pretty silly. We look at our VIFs. The VIFs are officially horrible. So 700's massive, 560's massive. Multiclinearity is a huge problem in this data set. All right. There are two ways to fit a ridge regression, at least two ways that I know of, in R. One is, I call it the old way, which is with Brian Ripley's mass package. So I like to start out with mass because it's very similar to LM. So it takes a formula. You can give it, okay, I've standardized the data. You're going to see I use the scale command to standardize it. The only thing that's new about it is you have to specify your lambdas. So here are my lambdas. To be consistent with the textbook I used to use, I'm choosing a sequence of lambdas where I start out at 0 and I go all the way up through 0.4. So 0.4 is a fairly big lambda. Now, when you fit this model, you are going to get a matrix of coefficients. So let's go look at this. Here is your matrix of coefficients, and these are the coefficients for x1, x2, and x3, respectively. The first column, the row label, is the lambda value. So what you're going to see is this first row has no penalty whatsoever, and it's going to be fairly similar to what I had in the previous slide. The difference is I'm using standardized betas here. All right, now as I increase the lambda, so let's turn up lambda to 0.01. So I'm putting a very small penalty on it. You're going to see what happens is we have to shrink the length of the beta vector. And now we can really see how silly it was to have that big negative beta 2, because I can make my beta vector much shorter. Think about squaring this number and this number. Well, that's going to be like 18 or something, and that's going to be close to 9. But if I made this negative a little bit less negative, I could make this number much less positive, and the squared length of this beta vector is going to be much less. All right, well, let's keep dialing up our lambda. If we take it up to 0.04, you're going to see, well, the first slope is now just 1.4. The second slope is about minus 0.4. When you plot one of these fitted objects, from lm.ridge, you get a very famous plot called the ridge trace. So this is the ridge trace. And if you remember your colors in R, black is 1, red is 2, green is 3. So this black curve, this is really important to understand, so make sure you're following this. This is plotting lambda on the x-axis and beta 1 on the y-axis. So we start out at 4.26, we go to 2.69, and so forth. So you're going to see this coefficient slowly is going to 0. If I were to take lambda up to a million, this curve would get really close to 0 because the betas would have been shrunk to basically 0. Now look at the red curve. So the red curve starts out at minus 2.92, and we eventually actually see a sign flip. So it becomes positive again. In the olden days, people, textbooks would say, well, choose lambda when the plot stabilizes. So maybe 0.1 to 0.2, this graph stabilizes. But that's very much the old way. The new way, as we're going to see in a minute, is to use cross-validation. Before I do that, though, let me just show you another function that we're going to use a lot in this class called glimnet. So glimnet does a lot more than lm.ridge. It's going to be used for the lasso and other methods. So what you have to remember is that if you want a ridge regression, you need to set another parameter called alpha equal to 0. All right, so let's not get into what alpha is right now. Just remember, alpha equal to 0 means ridge regression. So another thing that's slightly confusing about this is it doesn't take a formula. It does not take a formula. You must specify an X matrix and a Y vector. So to fit the same model, I now have the first 3 columns of the body fat data set, data frame. Can't give it a data frame. It has to be a matrix, so I've cast it as a matrix. Second argument you're going to see is my Y vector, so body fat $Y. This is saying I want to do ridge regression, and I'm passing it a set of lambdas. Now if you do this, you'll get a plot that matches what we had from lm.ridge exactly, and you can also get a log plot. Now, remember I said you can do this with cross-validation, and so that's a much better way. So go back to this picture. How do we decide on the optimal fit? Well, we look for the minimum value of the test set. Minimum error in the test set. So there's a function that goes with glimnet called cv.glimnet, where I can indicate the number of folds. The default, I believe, is 10. I chose 5 for this particular data set. Now, what's happening here is R is going to go fit, for a variety of lambda values, 5 different models, leave out one part, score the left out part, and then produce, cross-validation estimate. So this is going to be cross-validated mean squared error, and this is kind of the equivalent of this plot that we have here, except they didn't go far enough for the thing to actually start going up again. But they found what they think is the lambda min, and you're going to see the lambda min is 0.0855. If you take the log of that number, you should get whatever this line is, so minus 2 point something. If you don't believe me, let's just go try that in R for a second. I'm going to take the log of that number, and we get minus 2.45, so that's about where we are here. All right, so that's how we can fit a, to find out, again, go back to this picture. Where is the bottom of that? The answer is we need a lambda 0.085 something or other. All right. I'm not going to do this case right now. I'm going to instead move on and just talk about a different way of regularization. So another way to regularize or shrink these coefficients is to, instead of adding up the sum of the squared lambda values, we're going to sum up slightly different penalty. It's the sum of the absolute value of the lambda values. So if you think about it, let's go back to my PowerPoint. This is something called the taxi cab distance, or the L1 metric. So let's say I want to get from here to here. If I do that as the crow flies, that's the Euclidean distance, and you have the squared distance is b1 squared plus beta 1 squared plus beta 2 squared. But if I add up this length plus this length, and so that'd be like, if I'm in Manhattan and there's a big skyscraper here, I'd have to take a taxi here, then I'd have to take a taxi up there, and that's why it's called the taxi cab metric, or the Manhattan metric. All right, now this metric has a very important property. The property is that I've written it out here. The lasso tends to force some coefficients to equal 0. So it's going to shrink some and it's going to zero some out. For an explanation of this, go to your textbook. And this is page 222, and it gives a beautiful explanation for why some of these betas, in this case beta 2, get zeroed out. Whereas with ridge regression, all of the coefficients will be non-zero, although many of them will be quite small. All right, so what's really important is that if you want a parsimonious model, the lasso penalty is going to be for you. If you don't think that you want coefficients to be zeroed out, ridge will be your model. In practice, we don't often know, so we'll just try them both and see which one does better on a test set. All right, so that's what Lasso does. There's an example, this college case, that we will do in another video.